So good afternoon, everybody. Welcome to second edition of the Heidelberg Joint Astronomical Colloquium of 2024. Good to see so many people coming down from the hill. And it's my pleasure to introduce the topic today, which is more on the sort of data analysis side. But as you know, this is right at the forefront of science. And we have one of the world's foremost experts on this today, Roberto Trotta from Trieste, to tell us all about it. And for the formal introduction, please come across Evelina and introduce.
Hello. It's a great pleasure to introduce Roberto Trotta today. This visit has been very, very long in the incoming. Roberto is a theoretical cosmologist at the International School for Advanced Studies in Trieste, Italy, where he's a professor of theoretical physics and the head of the newly established group in theoretical and scientific data science. He has previously held research positions at a number of institutions, including University of Geneva, the University of Oxford, as well as visiting positions at the African Institute for Mathematical Sciences in Cape Town and University of California at Santa Barbara. He is the recipient of numerous awards, including the Michelson Prize of Case Western Reserve University, the Lord Kelvin Award of the British Association for the Advancement of Sciences, and a Public Engagement Fellowship by the Science and Technology Facilities Council in the UK. His research focuses on the developing and applying of advanced statistical methods to a variety of problems in cosmology and astroparticle physics. He's the author of a number of numerous research papers and two science books, including a recently published Starborn. You can ask him all about that at drinks and dinner after the colloquium. Please let me know if you'd like to join. And now I'll give the stage to Roberto.
Thank you so much, Evelina and Richard, for the warm welcome despite the icy conditions. It's really nice to be here and already had this wonderful 48 hours by now here in Heidelberg, and already had a number of fantastic discussions around the topic of machine learning and all the science and astrophysics and cosmology and astronomy that goes on here. So really wonderful place to visit. Today, I'd like to give you a little bit of an overview of what I think might be one of the frontiers of machine learning, namely this idea that cosmology is now entering a data-driven regime that will require new and advanced methods that will go beyond what we've been doing very successfully for the past 20 years or so. And machine learning might be one of the answers, but with some conditions attached. In particular, I will use supernova type 1a as a case study, although the methods and the ideas are general, and I hope they might be interesting and relevant and useful for many of the scientific enterprises that you're all involved in. In particular, I will talk about two different aspects. One is simulation-based inference, which I think might be the next level of inference methods that we will be deploying on the next generation of data. And then, time permitting, I will talk about a general solution for a very widespread problem in astronomy, covariate shift, when the training data are not representative of your test set. But before I do so, I'd like to just spend a minute introducing the wonderful group of people I'm privileged to work with in Trieste at SISSA. This is a data science group that Evelina mentioned earlier. It has been founded 4 years ago, and it's very broad. In fact, my group is interested in astrophysics and cosmology and astroparticle physics, but the group as a whole has a much larger interest in various domains in science, including bioinformatics with Guido Sanguinetti SPI and the theory of neural network with Sebastian Gold. And we are really interested in that cross-disciplinary liminal space where different machine learning data science methods can be brought to bear to different scientific problems. And we very much hope to continue developing these machine learning methods and to apply them at the forefront of our different fields of expertise. Much like I see being done here, cross-disciplinary work is very, very important in my mind. And that's something that I'm very happy to be part of at SISSA. So just to take a step back, especially for the non-experts and non-cosmologists, how do we get to the place where we are in terms of data-driven discoveries in cosmology? When we think about astronomy in particular, sometimes we think of astronomers, not you, but people outside think of astronomers as this, right? People looking through a telescope. I like putting up a picture of Vera Rubin in the 40s because that's not the picture we often see, a woman astronomer, because there is not enough of women in astronomy today. Fewer still in the past, but they've done fantastic great contributions to the field, and they're often, if not neglected, a little overlooked. So I like to talk about Vera Rubin as an an exemplar of the old school astronomer. Of course, nowadays, hardly anybody looks through a telescope anymore. This is the kind of state of the art. Telescopes that are, in this case, the ground-based LSST, the Vera Rubin Observatory, which will soon have first light, an 8.4 mirror with a camera of 2000 megapixels, which will image the entire night sky of every 3 nights. And so the science goals of the LSST are very, very broad. But you can imagine when you have a machine capable of imaging in many different bands the entire night sky over three nights, you're going to look for transients, you're going to look for all sorts of things that previously nobody ever imagined were out there. And you're going to need a great deal of computational, statistical data analysis power to even make sense of this large amount of data. Another example in space, the Euclid Space Telescope, of course, launched very recently. You will have heard about it. A 1.2 meter mirror with a camera of 600 million pixels, and will be able to image up to 10 billion sources and get spectra for some of them, 1 billion galaxies for weak lensing analysis, and something like 30 million redshifts. So those are really impressive numbers that will take cosmological studies to a different level of complexity. And the sheer size of this data is taking our game in cosmology and in general, sort of astronomical, astrophysical data analysis to a completely different level. And we can gain a more historical perspective by looking at the number of objects known to humankind since, well, let's say since Galileo, since the invention of the telescope in 1600. And you see that as a function of time, the number of objects remain pretty much flat, if you will. There is not much happening here until, well, until the photographic plate is discovered, or not discovered, but photography and plates are being used in astronomy at the beginning of the 20th century, and you can start seeing, the number of data points, number of data really creeping up massively until, of course, the turn of the millennium, where the CCD camera becomes ubiquitous in astronomical study. And here again, you see this vertiginous exponential increase in the number of objects and number of sources that we see in the sky. And with Euclid, with LSST, with Gaia, we are taking this again orders of magnitude above the level here. Maybe I want, because I mentioned photographic plates and I mentioned the history of astronomy, that's another perhaps not so well known aspect of it. When photographic plates were all the rage at the turn of the century, and those were sort of what CCD cameras and machine learning is doing for us now, we needed people to analyze them and look at them one by one and measure the brightness, the variability, the color of stars, galaxies, and so on. And at Harvard Observatory, which was then the leader in sort of photographic exploration of the universe, women computers, as they were called, were at the forefront of that research. And I see a group of women here who were engaged in analyzing hundreds of thousands of sources by hand, and they used an instrument you see on the left, the so-called fly spanker, because it was a calibration device. Essentially, you would look at the star or the galaxy through the fly spanker, and that had little calibration dots that you can use to judge the brightness of the source by. It was called the fly spanker because it was so small as it could be used to swat or even spank a fly. And I mention this because, again, this is a contribution to history of astronomy that sometimes we neglect to say, but people like Annie Jump Cannon personally classified something like 200,000 stars over 40 years of work, at 30 cents per hour. So that's quite some achievement, and we shouldn't forget all of that. Nowadays, of course, it's all the data come from remote places like space, like the Karoo Desert for SKA and the outback in Australia, like Antarctica for particle detectors like the IceCube neutrino telescope, and all of them produce large amount of data like the ones that I mentioned earlier. And this feeds into very complicated statistical analysis for which we need supercomputers and high capabilities, even just to make sense of this data. So the bottom line is that we're rapidly approaching a point where our capabilities to learn about whatever science we're interested in doing is no longer limited by the amount of data. Indeed, the amount of data is becoming the bottleneck. The bottleneck is, how to make sense and extract information from this huge amount of data. And we see it across domains, across wavelength, across different kind of physics. Here's an example from the cosmic microwave background, which used to be my first love in cosmology and my first field of study. That's what I worked on for my PhD 20 years ago. And the resolution went from Kobe maps to Planck maps, increasing many folds over 20 years. And every new generation of instruments, spaceborne or telescopes on the ground, brought new data analysis challenges, new high resolution, higher complexity, higher information content that needed to be extracted with more and more sophisticated methods until we get to a point where the state of the art, my cosmic microwave background power spectrum, this is the temperature power spectrum as an example, is really, well, beautifully measured. Of course, you see the error bars are tiny and very well characterized. And by now, standard data analysis techniques like Bayesian Markov chain Monte Carlo give us very, very tight constraints on cosmological parameters, sub-percent constraints, by matching what is a very simple model of the early universe, which is based on inflation, primordial fluctuations that are largely Gaussian, and essentially linear perturbation in the early universe. The prediction is very, very robust, very, very well understood because it's low energy physics. And we can fit this kind of data at high redshift. Those are data coming from redshift 1100. So very, very high precision, but also relatively easy to model because of reasons that I mentioned. Those are small perturbations. Linear physics is enough, low energy, all stuff that we can understand very well. Unfortunately, if we want to go to the next generation of discoveries, the CMB, well, will have more to tell us, but it's been largely mined, and the easy part is done, and that's a great success, for cosmology. But for the next generation, we need to turn our attention to more difficult things to study, evolved objects, things that have undergone gravitational collapse, things that are uncertain because of baryonic feedback or baryonic physics that we don't understand as well as the simple plasma in the early universe. And so in the domain, for example, of large-scale structure studies, again, we see the immense evolution from the 70s to today, where the state-of-the-art De Vaucouleurs et al. Galaxy Atlas in 1976 was a book, an actual physical book with 4,000 tables with 4,000 objects on it. 1998, the CFA2 sample was on the order of 20,000 galaxies, and by 2020 we were at the level of few 10 to the 5 galaxies with SDSS and BOSS and other large-scale surveys, all of which again powered by CCD cameras and the fact that we can now image the sky so much more quickly. And here's another example, supernova type 1a, or this is our supernova discovery, not necessarily just type 1a. Again, as a function of time, you can see an impressive uptick here around the turn of the millennium in the number of objects discovered. That's a logarithmic scale. It goes up when the CCD camera became the way to discover those objects. And in 1996, the discovery of cosmic acceleration using type 1a supernova used 42 objects. Nowadays, the state-of-the-art sample with spectroscopy is of the order of 2,000 objects. But with LSST and Vera Rubin, we'll get something like 1 million supernova candidates a year. Right? So it took 20 years to assemble 2,000 good objects for distance measurements using standard candles. And now we're going to get this huge number of objects a year. What are we going to do with them? How are we going to use them to learn more about cosmology? And so this has been a very successful program. And we now have a great deal of observation stretching from the early universe, 380,000 years after the Big Bang with the cosmic microwave background, through large-scale structure, through evolved objects like supernova type 1a, Lyman alpha forest is very much coming into the limelight now. But the fact is that this leaves us with a very, very complicated conundrum, because we know that 95% of this universe remains unexplained, 30% or 25% dark matter and 30% dark energy. And if you're interested in understanding more dark energy in particular, then we must look at the evolved universe, at a contemporary universe some 5 or 6 billion years ago. And that's a universe that has undergone collapse, where you find galaxies, clusters, astrophysical objects of various kinds that you can use to trace the expansion history. And those are much more difficult to model because they're simply more complex. And so studying dark energy will require meeting those analysis challenges that were mentioned before. What we've done so far has been really successful. I can say that precision cosmology is now a thing, largely because of this man, Thomas Bayes. I mean, Thomas Bayes, of course, never dreamt that these ideas would be used in the way they are now. And in fact, it's funny because if you look online, you look up Thomas Bayes online, you'll find this picture as the portrait of the man who's a Presbyterian priest who lived in 18th century in England. not a cosmologist, of course, he was a mathematician or almost amateur mathematician, I would define him. And the thing is that as one of the founder or the reputed founder of the major branch of probability theory, I find it funny that this one picture of him that is available online is of uncertain origin, quite fittingly so, I think. And so this might or might not be Bayes. The thing is that Bayes' theorem, about which many of the statistical techniques are based, is deceptively simple and really almost trivial, because it follows from the basic rules of probability. You can write the probability of two events A and B, the joint probability of P and of A and B, as a probability of B given A times the probability of A, or vice versa, probability of A given B times the probability of B by symmetry. And then you just rearrange this equation and you get this equation here, the probability of A given B, written as a function of the other condition, the probability of B given A, and the two marginal distributions, which is Bayes' theorem. Really simple, incredibly trivial. And it becomes really interesting when we now replace A with the parameters of the model we're trying to learn, and B with the data to obtain this formulation of Bayes' theorem down here, which tells us the probability distribution for the parameters given the data, what we call the posterior, is proportional to the likelihood, the probability of the data given the parameters, times the prior, which is the probability of the parameters alone before we saw the data. And that is at the heart of much of the data analysis that we've been doing for the past 20 years. Certainly, all of the CMB data analysis that I showed you relies on that. And it's a powerful tool, a simple and powerful tool, which encompasses a more general definition of probability. So probability as a state of belief and state of credence, which has got a very straightforward intuition. The left-hand side of this equation really is a probability distribution on the parameters, which the likelihood is not. It includes prior information when it's available, but also it unlocks efficient exploration of parameter space via methods that go under the umbrella of Markov chain Monte Carlo. I want to go into the details here, but this is something that we've been doing for many years. We've been very successful at doing it, not just in cosmology, but in many branches of astrophysics as well. But the message I'm here to tell you today is that these methods, facing the avalanche of data that I described, are now almost getting to the limit of what they can do because of the dimensionality of the parameter space that we have to face. And that's where, hopefully, machine learning might come to the rescue. So whenever you see something like this, parameter constraints in a omega matter, omega lambda plane, dark energy on the or cosmological constant on the y-axis and matter on the x-axis. This is recent constraints from the Dark Energy Survey collaboration, merging various kinds of probes, including baryon acoustic oscillations, supernova type 1a, cosmic microwave background, and so on, and then zooming into a very tight constraint on the cosmological parameters. Whenever you see plots like this, Bayes' theorem has been used in some way to get to this kind of marginal constraints. And it has been used by specifying a model for the data. Each one of these data streams has got a model for how they've been generated from a cosmological model. Specification of the likelihood, what is the noise, and what is the data, the aleatoric way in which the data are generated. MCMC as a sampling procedure to get posterior distributions for the parameter. And then, crucially, those are high-dimensional fits. So there's more parameters in these models than two, of course, but these two are the ones that we're really interested in, the cosmological parameters. And if theta is the cosmological parameters, then in Bayesian inference, what you do, you solve the full problem, where you solve the problem in terms of the cosmology and other parameters psi, whatever they might be, and then you integrate out, you marginalize out psi, like so. And this is simple to do and convenient to do with MCMC, and we've been very good at doing that. The problem is that nowadays, when we are now facing all of these higher data, higher numerosity data, so very large data sets, you might think you're going to win because statistics tells us that the precision goes down as 1 over the square root of n. If n becomes large, your precision is going to be very high. Your statistical error will decrease. That is true, but oftentimes this will be at the price of accuracy. So your statistics error will go down, but what we might call systematics will start to dominate, and they might actually give you the wrong answer. Oftentimes, we find that in order to write a model, in order to write a likelihood, in order to do the MCMC sampling that we need to do, we need to make simplifications so far. And those simplifications, here's an example again around type 1a supernovae, those simplifications are not so important when you got of order 10 to the 3 objects. The difference between the contours that you get if you simplify, that's a red contour, or you don't use another procedure that I will describe that is fully exact, or fully, not exact, but it encompasses the full complexity of the model. This difference kind of gets lost in the wash. But as you increase the number of objects, there comes a point in the near future when you have 10 to the 5 objects, and now the statistical error has gone down so much that the simplifications that you make in your model in order to be able to use MCMC and likelihood-based methods in red will drive you far away from the truth, which is the black star. And so this is something that we need to address if we are to get constraints on cosmology or any other quantity that we're interested in that are both precise and accurate at the same time. So really the questions I want to ask today are multiple, are questions about how do we extract the full information from the data sets that we are poised to gather? How do we include uncertainty in a full way in our astrophysical models? And how do we check the quality of what are often only numerical simulations? You can forward simulate the universe in many ways, from n-body simulations to hydrodynamic simulations to compact objects and so on. But how are we sure that those simulations actually encompass reality? And how can we do all of the above at scale, at the scale that we need to do in order to use all of this data? And that's where machine learning comes in. And the message at the end will be machine learning can help, but only if we use it in a way that is principled and coupled with what we have understood from statistical methods that have been tested over many, many years. In fact, this is a view of that process in my personal experience, slightly simplified cartoon way of how I've seen this work out in my field, in cosmology, where until around 2003 or so, what people used were likelihood-based frequentist methods that worked for the quality and quantity of the data that were available at that time, but started breaking down in the era of WMAP, when data became larger and parameter space is more complex. That's around the turning of the millennium, I think, with CosmoMC and other tools coming out, that the Bayesian revolution took place. And so in fact, you see all the number of Bayesian papers really starting to pick up in astronomy around that time, because people turned to Bayesian methods to deal with the problems that were untractable in other methods. And we're seeing perhaps that transition now again, but now going from Bayesian methods to machine learning methods, with again here around 2015 or so, people started to turn to machine learning as a way of addressing the problems that I've outlined. And I think this is where the field is going, but we need to be a little careful how we get there and make sure that we're not Google. So in a sense, our problems are harder than Google's, because Google is happy to be able to sell you stuff by using machine learning tools that will predict your behavior, your interests, and what you will buy or where you will click next. But we want more than that. We don't just want prediction, we want understanding, and that requires a slightly different approach. I want to give you an example of some of those tools in the context of a specific line of research, although, like I said, the tools are general. Supernova type 1a. And so in order to do that, for those of you who don't know about this field, I'll just give you a very brief introduction of what the scientific problem is and what are we doing with it, and how does it work. So supernova type 1a are a type of stellar explosions. Here you see, perhaps, a movie of a carbon-oxygen white dwarf undergoing a thermonuclear explosion, which brightens the supernova over a period of about 3 weeks. So the actual light curve, which you see on the right-hand side, is powered not by the explosion itself, which disrupts the stars in a matter of microseconds or milliseconds, but is actually powered by the radioactive decay of the iron group elements, radioactive iron group elements that are produced in the thermonuclear explosion. And the way we think this comes about astrophysically is in a binary system, in which at least one of the two members is a carbon-oxygen white dwarf, which somehow accretes mass via some mechanism which is poorly understood so far, either by accreting mass from a companion star, a non-degenerate main sequence star, for example, a red giant, like on the left-hand side, or a binary system made of two white dwarfs that loses energy to the gravitational wave emission and then eventually merges. Be as it might, once the mass of the carbon-oxygen white dwarf approaches the Chandrasekhar 1.4 solar masses mass limits, the pressure on the nucleus increases to the point that the thermonuclear reaction sets off and carbon ignites with a deflagration and explosion ensues. And the point is that because there is this 1.4 solar mass threshold, which is a physical threshold for when the explosion occurs, you can surmise that at first order, the amount of radioactive elements that are produced in the explosion will be of the same order of magnitude. And therefore, the intrinsic brightness of the object will be approximately the same. And if that was the case, then you could use this as a standard candle, as an object on which you know the intrinsic magnitude, you measure the apparent magnitude, and therefore you can work out the distance. Things are not quite so easy, as they never are, because if you take calibration supernovae, you see the light curves here on the left, and you plot their absolute magnitude as a function of time. This is the quantitative view of the light curve. You see that the scatter of these light curves is quite large. There's a couple of orders, there's a couple of magnitude scatters. So those are not really standard candles. There is variability, intrinsic variability in these objects. But you perhaps also notice from this plot that if you have a supernova here, which is in absolute magnitude brighter, it takes a longer time to decline, while supernovae that are less luminous fall off much more quickly. So this was discovered by Phillips and others in the 90s. So if you measure the decay time of the object, you can work out the correlation between the intrinsic brightness, the intrinsic magnitude, and the decay time, and correct for it to the point that you can then map all of the light curves onto a universal light curve with the dispersion you have the peak much, much reduced of order 0.1 magnitudes. And that makes them standardizable candles. And if you now have the flux and you know the brightness, or you know they are all the same, you can work out the distance as a function of redshift and cosmological parameters and work out cosmology. And that's how Rees and Perlmutter and collaborators got their Nobel Prize in 1996. So I want to use this as a case study because that exemplifies many of the problems that we face and will face in terms of statistical inference. The name of the game then is to plot a Hubble diagram like this, where you got redshift on the x-axis, you got essentially log distance on this axis here, which you infer by the process that I briefly described, although of course the details are more complicated than that. And what you want to do, you want to be able to distinguish between different cosmological models, which are models that are from simple theory, relate the distance to the redshift to distance. And you can see that here, in order to do that, you have to go at high redshift over redshift 1 or above. And at high redshift, the difference between lambda CDM, which is a model with 70% dark energy, 25% dark matter, and a model with no dark energy, which is the green line, is about 0.2 magnitudes. And the scatter of the objects is quite big. So unless you bin those things or you use some statistical analysis, you won't just see it by eye. Remember, the intrinsic scatter of the objects is 0.1 magnitudes. So this is not an easy problem. And the devil is in the statistical detail. So now the state of the art of this game is about 2,000 objects, but this is set to increase by orders of magnitude in the next few years. And of course, then you can play this game in various ways. You can extend this distance ladder backwards towards closer to us, see fits variables here, and parallax measurements there, and work out the slope of that, and that gives you the Hubble constant, which is famously in tension with the CMB. So the local Hubble constant, the Hubble constant for local measurements seems to be at pi sigma odds with the one that you infer from the high redshift measurements, the famous H0 tension, which at the moment remains unexplained. And so doing those things right really is important, because it might either give you, systematically wrong results. This was the case here, I don't know, or it could uncover new physics. If H0 is different locally than what you infer from high redshift measurements, that's really important. It would point to new physics, perhaps in the early universe. The way we've been doing this so far, before I move on to telling you about the way I propose we'll do it from now on, is by using highly sophisticated or increasingly sophisticated Bayesian hierarchical methods, whereby the data down here, which is the light curve measurements that I showed you, are modeled in a fairly sophisticated manner by embedding them in what is a hierarchy of statistical relationships called a Bayesian hierarchical model. And so at the top here of the model, you got parameters describing the cosmological model that you're interested in constraining. That's how much dark matter, how much dark energy you have, the Hubble constant, and so on, with the prior distribution. You also have parameters here that describe the population distribution of the supernovae, how their intrinsic brightness is distributed across the population of objects, for example, and other nuisance parameters that have to do with the standardization procedure that you need to make in order to put them all on the same curve, which you need also to infer from the data. So if I tell you what those parameters are, psi, theta, and phi, then I can predict what the value of the fluxes will be here on Earth after, I take into account all sorts of effects, of course, redshift, reddening, and absorption by local dust, cosmology, of course. And then I have to add noise and perhaps selection effects due to telescope efficiencies and so on to produce a prediction for the data that I can then compare with the real data using a likelihood. This has been done in increasingly sophisticated fashions in a number of papers in the last 10 years. But one of the things that I want you to notice is this, that because here we got this model has got global parameters at the top, and it's got local parameters here. There is a plate here that runs over all the objects that you have. And if n becomes 10 to the 5, then you got individual object parameters here that you need to include, model, and at the end of the day, marginalize, that's to say, integrate over down here in order to get constraints on the parameter that interest you. And that's difficult. And it becomes increasingly so because of the dimensionality of the data and the dimensionality of the model parameters that you need to incorporate in order to model those objects faithfully. And so, like I was saying, we've been doing this in an increasingly sophisticated way. I won't go through the details of this is an actual Bayesian model that we've used. The details do not matter. But what I want to say is that the point is that we want now to go to a regime where we are drastically simplifying this approach because it's non-scalable. It won't be able to do 10 to the 5. And so what we propose to do here is to say, well, here we got a bunch of population parameters that we don't really care about what they are, but we need them, although we would like to get rid of them if we could. There's parameters for each supernova that, again, have to do with the astrophysics, that are not to do with cosmology. And then there is things that have to do with the instrument, noise, covariances, selection effects, again, uninteresting for us. What we really care about is the cosmology and the data. And we suggest to get rid of all of this by focusing on what matters, by embedding all of this in a giant simulator, just a numerical forward simulator that gets fed cosmological parameters and all of the other parameters that are relevant in the game, fed through a simulator that produces mock data. And by training a suitable neural network or other machine learning tool, I can get marginal posterior for the parameters that interest me. And once the simulator is trained, I'm going to plug in the real data, and I crank the wheel, and I will get cosmological constraints. And I will tell you later that this comes with the added bonus of guaranteed coverage if you care about coverage. And so the idea of simulation-based inference is to get rid of all of this modeling, get rid of the likelihood, get rid of all these parameters that you don't care about, and just focus on what matters. And so that's what I want to tell you in the next 20 minutes or so. How do we do this in practice? Ideally, this is very, very simple. It's called ABC, approximate Bayesian computation. If you were able to do this, you could just simulate from the prior, take parameters from the prior, run them through the simulator, produce data, some summary statistics of this data that you compare with the real summary statistics. And if you repeat that enough times, you just retain parameters values that are sufficiently similar with some distance measure from the real data, and you throw away the others. This will eventually is going to give you an approximation to the posterior. Unfortunately, in practice, this is not feasible. And it's not feasible because the summary statistics is typically high dimensional, and distances in high dimensions are difficult. You end up throwing away all the points. You never find anything that looks like the real data. So we need something else, something smarter. And that's where neural networks come in, because neural networks are, as we know, universal approximators. We might hope to be able to train a neural network. So in this process here, we're going to use the simulator to produce mock data to train a surrogate. And this surrogate will be a machine, a neural network that is trained to mimic, to approximate one of these three things: the posterior distribution, the likelihood, or another quantity, which I'll tell you about in a minute, the likelihood to evidence ratio, R. And if you have this thing that's trained, then we feed it with the real data, and it will spit out either the likelihood, the posterior, or the ratio, and we'll have inference. What is more, because this surrogate is trained from a region in parameter space that comes from the prior, it can spit out the answer with any data, in particular, not just the real data, any simulated data you care about. You can feed it to a trained neural network, and you'll get the posterior for it, which enables you to do calibration of your posterior coverage, for example, at almost no computational cost. This is what we call amortized inference, meaning that once you've invested the time to train the network, Now inference comes for free. It's milliseconds. So how do we do this in practice? Well, recall Bayes' theorem, which looks like this in the form that I showed you before. And now I'm going to introduce this quantity, this ratio here, R, which is a function of both the data and the parameters, which is simply the ratio of the likelihood to the evidence, the normalizing constant, which is also equal by Bayes' theorem to the ratio of the posterior to the prior. Yeah, which is a quantity that if we knew how to approximate, if we add R, if I add this function here, then I can just multiply by the prior, and by definition, I'm going to get the posterior. So now my problem is, how do I learn R from this training process? That's where neural networks come in. And we know that neural networks are very, very good. In particular, they've been very, very successful at classifying things, supervised learning of multi-class populations. For example, here, we've got a number of pictures with labels, and we feed them to a neural network with a suitable loss function and so on, cross-entropy loss. And we train the neural network, and then when the neural network is trained, I feed it a new data set and ask it to predict, what class is it in. It's a dog. So this is something that neural networks can do very, very well. And so we want to leverage this to transform the inference problem into a classification problem by rewriting the problem like so. So here we got our ratio here, which is the ratio of posterior to prior. I multiply by the evidence just because I can. And this quantity here is the joint distribution of parameters and data. And in the denominator, I got the marginal distribution of parameters and data. And now my R is just the ratio of two distributions, the joint versus the product of the marginals. And what I can do, I can generate examples of both. In other words, I can generate examples of parameters and data from the joint distribution by generating examples of pictures of cats with correct labels, picture of dogs with correct labels, and so on. Those are positive examples where they come from the joint distribution. And the negative examples are the ones that come from marginal distribution. So pictures that are pictures of cats, and I randomly sample from the other distribution, they do not match. And so I train a classifier to distinguish between these two categories. If I can do that, the classifier can be used to learn R. And once I have R, I got the posterior. This is called marginal neural ratio estimation. And it's called marginal because, as I told you before, we don't want to solve the whole problem if we can help it. We want only to solve the problem that interests us. In fact, when you have a large dimensional parameter space, here's one example, typically you have to find the joint posterior for everything, just to then marginalize everything out, integrate out everything that you don't care about to get a two-dimensional posterior for the things you care about. Why do so? All we need to do in marginal neural ratio estimation is to train a separate network to learn only the subgroup of parameters, say two-dimensional subgroup of parameters that we're interested in, and ignoring everything else. And we train as many neural networks as we care to have groups of parameters in parallel from simulations of joint or disjoint pairs of examples from the simulator. And we call this truncated marginal neural ratio estimation. What is more, once the network is trained, you can show it examples of data, and you can check the posterior distributions for coverage. How many times do you actually cover the true value that you know from the simulation? And so, for example, in this example on the top left, you see that in this case, the posterior distribution is too large because the truth should fall out, if you care about coverage, 68% of the time for the 68% region. In this case, it falls out fewer times, so that those regions are too large. Vice versa, the regions can be too small, and you can assess that by simulating many data sets and checking what is the actual coverage. And then you can invent a procedure, statistical procedure, that will correct the regions that are too large, that will be shrunk. If they're too small, they will be widened in such a way to get exact coverage. In other words, your 1 sigma region by design will guarantee that the truth is inside 68% of the time. Okay. So we've done that. The details are not important. We can produce coverage maps such as the one that you see here that enables us to correct for under coverage or over coverage from the amortized simulator. And we end up with constraints that are like this, where you see the green regions are confidence regions with exact coverage by construction. So whatever the parameter space, whatever the truth parameter is, shown by the yellow star, we can guarantee that our posteriors will have exact coverage by construction. We've applied this to a number of problems so far: supernova type 1a inference, gravitational waves, ring down inference as well. An early example is shown here, and we found it very, very effective. And what we can also do with this approach, we can move on and do the harder problem, the one of Bayesian model selection. So now the game is to choose between different models. What if you have different models for your data on the table? And in Bayesian terms, this is done by looking at this quantity here, the evidence, which we have ignored so far because for Bayesian inference, the evidence is just normalizing constant, is nothing else but the integral of everything that's up here, the likelihood times the prior. But in Bayesian model selection, what you do, you can write down the posterior distribution for a model. If you have different models on the table for your data, this is simply given by the model likelihood of the evidence times the prior on the model divided by this quantity here. And when you take the ratio between posterior distributions, posterior probabilities for the models, it's called posterior odds, you'll find that they are the ratio of the evidences, which is the base factor, and the ratio of the priors. And so if you have the evidence or the base factor, you can transform your prior belief into the models into a posterior belief, updating it through the data. This has also been done very successfully using traditional techniques, but the problem again is integration. You got this high dimensional integral that you need to do, which when theta is 10 to the 5 dimensions, there is no method that can actually do it. No traditional method can do it. We simply run out of, it's the curse of dimensionality. And we've developed a marginal ratio estimation method that, again, we've deployed on supernova type 1a examples that can do that in thousands of dimensions, simply by applying this forward simulation approach and assigning labels according to which model the actual data come from. We validated it with the true model class in 6 different models versus the one that is recovered by the algorithm. And we can therefore bring Bayesian model selection to bear on problems that have thousands of dimensions, including many, many dimensions that do with individual objects that you don't care about, but you need to include in order to get the correct inference on the parameters that you care about. So that's where I think we're going with simulation-based inference. I think it's going to be a very powerful, very useful tool for the next generation experiments. In the last 10 minutes or so, I'd like to tell you something different. Another aspect of data analysis and supervised learning in astronomy that I think is quite widespread, and I think many of you might find relevant and useful for some of your work. We talked about supervised learning, giving examples of things, but of course, we know that your trained network, whatever it does, is only as good as the quality of the examples that you give it. In particular, and those are some examples from real life, even big corporations like Google got wrong-footed by this in the early days of machine learning. This is from 2015, where tagging methods that were supposed to be able to tag pictures automatically were failing in a very bad, very spectacularly wrong way by tagging Afro-American people as gorillas. And partly because the training set on which those things had been trained didn't have enough dark-skinned people in its sample to recognize correctly this kind of input. And even in 2018, the problem had not been solved. The solution that initially Google found was to take away the tag gorilla from the options because they couldn't find a good solution for it. And as late as 2019, facial recognition systems suffered from the same bias. White males, accuracy of facial recognition was much, much higher than for black-skinned females, again, as a consequence of the bias in the training sample of the algorithm. In cosmology, those are very, very important and very, very dangerous things in society, where machine learning is applied blindly with bad consequences for people. In cosmology, we don't have that, but still, we have a problem, for example, here, where your training sample for supernova type 1a classification is in black as a function of R-band magnitude. Your training sample is typically much shallower than your test sample because you need spectroscopy, and that is flux limited, and it biases your training sample to low magnitude, to high magnitude and low redshift. And the test sample is much higher redshift, so the classification is poor. You see, a random classifier is a diagonal line, and so if you learn something here, the generalization in the blue to the blue test set is poor. And that's ubiquitous in astronomy because of selection effects, the fact that we are flux limited in some way, And so here is again an example where you have objects that are supernovae as a function of redshift, and this is the detection threshold of the observed flux in the B-band magnitude. At some point, the fainter objects that start falling out of your detection window, and you miss all of these gray objects, and you only see the blue ones. And that means that if you only base your inference on the blue population, you would infer the blue curve, the blue Hubble diagram, but the true one is the red one. And so you bias your inference because you're not taking into account the fact that you're seeing a subpopulation which is influenced by selection effects. And in particular, when you're trying to do classification of supernova type 1a, what you would like to have in feature space is a training sample that looks like this, 1As, not 1As, with nice spectroscopic data that are homogeneously representatively distributed everywhere in your feature space. But what you actually have is something like that, where you have separation of classes which do not intermingle, and you have a region here at the faint end of your sample where the spectroscopic selection efficiency kills your training set, and you don't have many, if at all, samples from which to learn. And that leads to poor performance, poor generalization. So how do we solve that? Because, like I say, machine learning is great, but only if you can trust it, and only if you can have results that apply to your test set equally well as to your training validations. In statistical terms, this is a problem known as covariate shift. And in general, we can explain this by, in very general terms, by saying that we have a feature space, X. Those are the things that you measure. And you have a label space, Y. This could be a classification problem or a regression problem. It doesn't matter. You got labeled samples from your training set, which are called S for source, for which you have the input, the covariates, and the output. And you want to learn the relationship between Y and X. And then you want to deploy your machine learning method onto a test set or a target set T for which you don't have labels. And covariate shift, which is the case that I described a moment ago, occurs when the conditional distribution of the Y's given the X's is the same in target and source. So it's the same model, but the marginal distribution of the covariates, the samples that you actually have, is different between the source and the test. So the case is this one, where the source domain is non-representatively shifted with respect to the target domain. Various methods exist to undo this bias, but they're typically noisy and they're typically poor performing, especially in high dimensions. We propose this idea called propensity score stratification, or strat-learn for short, which is a super simple, super general idea, which we found is very, very effective. And the key idea is to define this quantity called propensity score, E, which is the probability that an object I is selected into the source domain. So if you're looking at galaxies, what is the probability that this particular galaxy with a particular bands would be selected into the training set? And you can build a model for that probability. So the probability of it being inside the training set, given the covariates, which you can do with logistic regression. And the key idea of strat-learn is to stratify both the source and the target domain according to propensity scores in quantiles of the propensity score model. And then we perform supervised learning inside each of the groups separately. Why? Because there is a theorem from the 80s that shows that conditional propensity scores, to say within the propensity score quantiles, the distribution of the covariates is approximately balanced, which means that covariate shift is approximately eliminated within the groups. And therefore, because under the covariate shift scenario, this is true, we get a good estimation of the joint distribution and we get a better generalization. Let me give you an example of that works in 2 dimensions, how it works, and then I'll close here. If you understand this, then you understand covariate shift. Here, the idea is a very simple example in 2 dimensions where you got 2 covariates. So this is our X, 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 and we want to do a classification problem. So we got data. This is the test set. We want to classify red from blue. Of course, in the test set, we don't know red and blue, so everything is gray in the test set. We get given a training set, a source set with red labels and blue labels. And the problem is that there is a selection function here along the diagonal line. And so we get more points here, but then we get fewer and fewer in this direction. And we end up with something that looks like this. So if I just use my linear classifier, if I learn what is the decision boundary between red and blue with a linear classifier on this training set, I'm going to end up with something that looks like this line here. But of course, this line here is going to do a very poor job on the test set. If I classify red and blue according to the gray line, I'm going to make a lot of mistakes down here. Stratified learning does the following. It creates a model for how the selection function leads to different probabilities for different objects to be admitted into the test set. So objects in group 1 have high probability of being in the training set. Sorry, admitted in the training set. Group 1 has got high probability of being in the training set. Group 5 has got a small probability in being in the training set. And then we train a classifier within each of the subgroups separately. And we then deploy the 5 classifiers to the right subgroup in the test set. And that ends up with these 5 different colored lines as decision boundaries, because each one of the learners has learned a decision boundary conditional on it being inside group 1, 2, 3, 4, 5. And you can see that indeed those new boundaries follow closely the actual separation between the points. And because we've been able to learn things conditional on the different propensity scores. And if you deploy this in high dimension, that's really, really useful, because in high dimension, you have no idea where those boundaries are, and the stratified model learns it for you. And so I'll just end by giving you a couple of examples. We use this on supernova type analytic classification, where we have outperformed all the other methods that are based on whatever method that is not data augmentation method. We used it in photometric weak lensing tomography, where we deployed it on 20 million photo-Z simulated in 9 bands with 21,000 spectroscopic training samples with covariate shift between the spectroscopy of the training set in red and the actual true value of the photometric test set. In this case, we know the truth because it's a simulation. And we find a factor of 2 improvement with respect to state-of-the-art methods in reconstructing the actual density distribution of the redshift of these objects. And we're applying it in the framework of photo-Z estimation. So learn how to learn photo-Z from photometric data alone based on a biased training sample for which you have spectroscopy as well. And here again, we find no bias, smaller root mean square error, and smaller number of catastrophic outliers when applied to simulated data that are expected of the kind that is expected for LSST. So just to conclude then, I think we are going towards a direction where the cherished old style Bayesian methods are starting to fray at the end. And we will all sort of need some machine learning that we can trust in order to be able to infer the things that we want from the right amount of data that we are going to face, which are both large and complex at the same time. Simulation-based inference is a promising avenue to do that because it can scale to very large data sets. It can take on as much complexity as your simulator is able to reproduce. And it's very effective because it gives rise in certain ways to exact coverage guaranteed posterior intervals, which is a perhaps desirable feature. However, when we talk about machine learning, we also need to make sure that the generalization will be good. And in supervised learning, sometimes this is not the case. And strat-learn is a particularly powerful, I think, methods to account for covariate shift, which is pretty common in astronomy. And so my final message is machine learning is the future, I'm sure, but it's a future that we need to be wary of because there's many limitations still. We cannot just leave our inference and our scientific conclusions to this black box. There's still much space, and even more space, I think, for principal statistical methods coupled with machine learning ideas to be able to tackle the challenges of the next generation of data streams. Thank you.
Thank you so much, Roberto. That was really a fascinating insight to what is from your description, and in reality, a really interesting and fast developing field, happening surprisingly recently.
Yeah.
And interesting to see that it's in response to all we're living in a golden age of data analysis as well as our technological ability to look at distant regions of the universe, and one has the feeling this is the mother the two are linked, of course. It's very, very, very interesting. Well, please, questions from the floor. Who's going to be the first?
I think the first question is always the hardest. Let's start from the second, actually. Maybe.
All right.
I've got a second question.
Yeah, is there a second question? I think we have one from Ralph. You can tell us whether it's a first or second question, Ralph.
You tell me what the order is. Measurement uncertainties in this, right? I mean, you have done a bit by looking at the dropout rate if you have photometric limits and so on and so forth, but often you have much more complex uncertainties, right? You have data that come from different instruments, they come from different decades, they have all kind of biases. How do you include all of that stuff?
Yeah, that's absolutely a great question. I think doing this with legacy data of the kind that you described, very, very hard because you simply don't have the information you need to do it properly. So I would say don't do it. I would say focus on the next generation of stuff because on that, I'm not saying that you have full control, but you will have access to everything you need to have control over this kind of uncertainty. So it feels like it's a shame to throw away all of these hard-won data, different services and so on. But on the other hand, perhaps the case could be that with LSST, with Euclid, with all the rest, Grace Roman and so on, JWST, all of these legacy data are rapidly redshifting away in that their usefulness is being, in many cases, overhauled by the sheer amount and complexity of the new ones. Probably depending on the field, right? Might not all generally be true, but my sense is that in many cases, the new data are so much superior that we can almost just rely on them. But maybe you have counter examples.
So I fully agree, but sometimes you have, let's say, within Euclid or James Webb or whatever, you have drift. You have kind of changing response time depending on how the telescope looks and so on and so forth. And then you cannot throw away most of the data.
No, you shouldn't. You have to have control over all of that. Yeah.
But what do you do if you don't? Can you incorporate it?
I
mean, you can learn on the error and the uncertainty also. You can include that into your data set as an additional feature.
Yeah, you can. Yeah, because people are rightly worried about, what if your simulation is wrong or it doesn't capture aspects of drift in the instrument. But the same is true of likelihood-based analysis, right? Because even if the likelihood always contains some fudge terms that need to be adjusted and maybe need to be moved to account for these kind of things. And if that is wrong, you always have to calibrate it in some way. And this is no different. You could include, if you know that those things can happen, you can include them as part of the learning and learn them on the fly with everything, together with everything else. The problem is the unknown unknowns. But that is no different than likelihood-based, because if your likelihood suffers from a systematic offset that you don't know to model, you're going to be off no matter what. You won't be able to tell. So in that respect, I hear your concern, and I'm concerned about that too. But conceptually, at least, is no different than what we've been doing so far. It needs to be taken into account. We cannot imagine those things as magic black box. No, but it's the same, conceptually is the same as what you would do in a more traditional likelihood approach. Yeah.
Okay, another question.
So my question concerns the data analysis of very big cosmological surveys. So there's a big hope in serendipity that one discovers unusual things and outliers from the data.
Yeah.
And I'm wondering what your perspective from the point of view of machine learning is to do that.
Yeah. So I exclusively talked about one thing only, which is supervised learning here. But of course, this is one slice of what you can do and other methods, right? So of course, serendipity has always been very, very important in astronomy. Every time a new wavelength, a new instrument, a new capability has come in, we found out something new that nobody ever expected. And so, supervised learning has its limits. There are methods to, one thing, of course, to say, which is obvious, is that you can't just look at those things and discover anything nowadays, right? But there are machine learning methods that can do that for you. There are, you can call them anomaly detection, you can call them contrastive learning, you can call them one-class classification, whatever. There are methods that are designed to either look for anomaly, although anomaly, of course, is a very difficult thing because in high-dimensional space, almost everything looks anomalous in some sense. So you have to define what you mean by that. But there are also ways of doing one-class classification. For example, when you have some strange objects that you want to find more of to widen the population, understand them better as a group, you can input to the sort of neural network the fact that you're looking for things that look like something that it's anomalous and you want to find more of that. And that will give you a higher, it would select it down to other examples. So there are other techniques that can be brought to bear to sort of increase the probability of serendipitous discovery. I think we must learn to use these machine learning eyes and to trust those machine learning eyes, not blindly, but in a way that is controlled. So to know what are the limitations. Otherwise, you're right. We might risk overlooking things that we are not looking for, and that would be a shame. Yeah.
Okay. So are we prepared for the first question? Oh, I see that there is somebody online.
Oh.
What I'm going to do is read out this question and then ask you to answer it. I'll read it out on the microphone
Yes.
and then ask you to answer it.
Yep.
So this is a question from Kirill Maltsev to everybody. Question on how to avoid biased learning.
Mm.
What is the advantage of the propensity score method you presented compared to cross-validation?
Mm.
Is it more expensive?
Expensive or expensive?
Expensive.
Oh, okay. Expensive, more expensive? No, it's not more. Okay, first of all, it's not more expensive. It's not more expensive because it goes a little bit against the grain of what the usual machine learning lore is, which is to say, you got more data, you throw all the data, your problem, you just let the neural network or whatever figuring it out for you. No, what we're saying is you have to throw the right data to the problem. So by segmenting the problem according to propensity scores and learning in subparts of the parameter space, and combining the answer later, that's the way to learn. And so it goes against the grain, but it's no more expensive. Yes, you have to train 5 different models, but that's not a huge expensive thing. Now, cross-validation, it depends exactly how you want to use cross-validation for this particular problem, because of course cross-validation can help you in detecting whether you have large uncertainties in certain part of your prediction, and that's useful to know, but it doesn't help you to correct it. So it will just give you larger error bars in regions where you've seen smaller examples, which is useful, but it won't tell you how to go about getting a better answer. And so in that respect, cross-validation is a little fit for purpose in this case. What people do usually is they try to do some sort of density estimation and correct in the part of parameter space where you've seen few examples by a ratio of densities. That's very dangerous because this ratio of densities in parts where you don't have many training samples is typically very uncertain, very noisy, and we've got large weights from a very small number of points. This is precisely why we don't do that. We don't use this kind of reweighting schemes because they're noisy and inaccurate and oftentimes poor performance, especially in high dimensions, because we have a model for how these things actually need to be stratified. We avoid that problem. So in that respect, I think it's not more expensive and it's more powerful than both cross-validation and this kind of reweighting schemes.
Okay, thank you. Okay, the response came, I see the indifference. I see the difference. Thanks.
Thank you.
Okay.
Thank you for the question.
And there's another question. Well, we have limited time, but I don't see the other question, Yufeng.
Oh,
hand raised.
Yes.
Yeah. So, okay. Well, let's try and do this with a link. Ziad, could you open your microphone, please, and let us know your question?
Can you hear me?
I can hear you.
Okay. So I could have written it, excuse me. So, but the question is simple actually. So what you showed before, which was the missing supernova. So as I see it, you did not solve the problem with your method, right? We will still be not able to know which supernova are missing at high Z.
So you're saying it will not know what supernova are missing at high Z. Well, yeah, okay. So you're referring to this plot, right? No, not this plot. You're referring to this plot, yeah, right? Where you're saying the gray ones you miss them. You're never gonna know that you missed them. But if you have a model for how you miss them, you know that you're not missing them at random, obviously. You're missing them in a specific way with a selection function that depends on the cosmological parameters of interest, in fact, and on the redshift and on the characteristic of the objects. If you add that thing to your model, you're going to be able to know that by measuring, let's say, only one supernova here is the tail end of a distribution that could have at the latent level many more supernovae, and so the model is able to figure that out if you know how you're going. If you know what is the forward model for selecting the objects. So in that respect, yes, you will figure out that you've missed a great deal of things, and your estimate will correct for that. Yeah.
Okay. Well, I hope that answers that question. I think we must wrap up fairly rapidly now. So unless there's anything really urgent from the hall, I suggest we leave further discussion until drinks or dinner later on today. On that vein, could I please have the overlay
Thank you very much.
to make a couple of announcements before we say goodbye for this time for Roberto. So it just remains me once again to thank Roberto. I'm not sure whether we really got to question number 1, but maybe home drinks. But in any case, it was a real insight, at least for me, and I'm sure for most of us all here online in the room here. So thank you very much for that very, very interesting and informative talk. Thank you very much.